Hello everyone, welcome to another webinar by Jscrambler, where we'll focus on the topic of protecting user data and mitigating data leaks. With this in mind, today we will cover a lot of ground, mentioning new attack vectors that are being used to leak data from websites and exploring different approaches that companies can put in place to prevent this. I want to start by letting you know that this webinar has been pre-recorded, so if you have any questions, you can reach out to us at hello@jscrambler.com, and someone from our team will get back to you as soon as possible. Well, today we have an excellent panel of speakers joining us. First off, we are joined by Jasvir Nagra, who is a security engineer at Dropbox and has an extensive track record working in application security in companies like Google and Instart. Jasvir is also a technical advisor at Jscrambler, so it's great to have him join us today. We are also joined, of course, by Pedro Fortuna, who is the CTO and co-founder of Jscrambler and has more than 15 years of experience working in application security, especially focusing on client-side attack vectors. And to close off this excellent panel, we have Don Duncan, who is the sales director of Eastern North America and Canada at Jscrambler. Don has an extensive background in software that spans companies like HP, MasterCard, and Shape Security. So I'll go right ahead and give the floor to Jasvir to get us started. Thanks, Jaz, and feel free to get the ball rolling.
Thanks so much. Hi, everyone. I'm really excited to be joining you all today. I'm particularly excited about today's topic because we're going to be trying to dissect a very complex security problem that's pretty dear to my heart. It's one that I've thought about for a long time and likely affects almost every organization there, which is the data leakage problem. And that is one of the effects of this broader class of problems that we're going to be talking about, which is the web supply chain attacks. During my time at Google, I led a team called Kaha, and my team and I foresaw a large number of the security implications that the increasing prevalence of third-party libraries on websites would bring about. I was personally surprised by how quickly these attacks evolved into the sophisticated web supply chain attacks that we see today, that are able to leak hundreds of thousands of user records from websites. So I'd like to start here by exploring why and how attackers manage to leak this kind of data from websites. Well, the first thing that we need to understand here is the anatomy of, say, an average modern website. When we look at some of the most recent stats, you see that around about 70% of all of the scripts running on an average website comes from third parties. In other words, only 30% of a website's code is actually written and maintained internally by the company. Now, even that number, 30%, is subject to some scrutiny, as we're going to see in a moment. But let's concentrate on this 70%. On the right-hand side of the screen here, we see a simple illustration portraying a typical website that is using some of the most common types of third-party scripts. We have things like a video player, analytics tools, form validation, and a live chat widget. This roughly averages out to about 35 third-party components and 41 in addition fourth-party components, which obviously creates a very complicated supply chain, as you may imagine. This supply chain gets so complex that it ends up creating a security blind spot, not only because we have all of these different services running at runtime, but also because the first-party code that teams are developing internally, those are also built on top of JavaScript frameworks or libraries like React or Angular or more esoteric ones, which themselves are developed and maintained by third parties. Not only that, internally to a company, you have sensibly varying degrees of experience in different teams. But when you add all of this up, you quickly get to the point where you have little to no visibility about the code that you are running on a website. What makes things worse is that many of these websites are constantly handling sensitive information like credit card details, you have social security numbers, you have private health information. When a user inputs and submits this data on any given website, it will invariably pass through the client side. So, putting everything into perspective, we're essentially passing all of this sensitive data through this chaotic void on the client side. Since we can't be sure any of these third-party scripts may try hard to intercept and leak this data, and not only maliciously, but innocently as well, because we basically have one giant ring, one giant playground where all client scripts play. Now, this wouldn't be such a big issue if the security systems that are widely deployed today were capable of protecting websites from this risk. But the traditional security tools that we have do not actually provide this kind of visibility or security or protection against these client-side scripts, which I'll talk about in a moment. So this is a critical problem that every organization has to deal with. I mean, we've always had to deal with, but the problem has become exponentially worse over time as companies have specialized and we rely more and more sensibly on third parties. But as a result, we also open ourselves to these third parties. The defenses that are most common today that are used to protect websites, such as browser defenses and web application firewalls, or even more modern things like using a content security policy, are just not enough to prevent at least one effect that occurs as a result of vulnerability to these supply chain attacks, and that's data leakage, effectively. But I'm going to let Pedro explore that later on. One other argument I've seen thrown around a lot, especially after this new executive order from the White House on improving cybersecurity, is vetting third-party code, doing code reviews of third-party code. And while vetting definitely, or code review definitely has a role to play in third-party risk management as a strategy, it's definitely not the definitive answer to this specific problem. Code review only shows you a picture in a point in time. What are the third-party scripts that you have on your page doing, what vulnerabilities they have, what is the quality of the organization that is producing this third-party code at a point in time. It provides little to no continuous protection in case one or more of these website scripts is compromised or suddenly starts leaking your users' data. The time frame between audits still leaves this wide opportunity for attackers to breach uh, our supply chain, if you even know what is in your supply chain, which itself is a question that is often open to debate. Take, for example, the MageCart web skimming attacks, where attackers leak credit card information. Whenever a user inputs into a payment form on any given website, a third-party script has access to it. Now, we've seen thousands of companies fall victim to these attacks. And on average, it takes around 22 days to detect the attack itself. So just the attack. During this time frame, the data of every single user that makes a purchase can be and is often leaked. So today we have more than enough proof that attackers are actively attacking these third-party scripts, and they're launching these web supply chain attacks. These attacks target the supply chain of websites and all third parties and fourth parties that we've talked about. By fourth parties, I mean scripts that are loaded by your third parties, which in turn may load other scripts or may be built out of other third parties to those sites, right? If you think about it, like you can imagine this large transitive closure of scripts loading scripts, or scripts being built out of scripts, that result in code from all of these different locations being loaded into your application when you're loading a website. And it's no wonder that this approach has been popular because it scales so well, right? Like from a developer's point of view, it makes sense to specialize, but it also means that if attackers manage to change a third-party script, they can basically inject arbitrary code into the website. And once they have done that, they can do whatever they want. This code will affect all users on your website and all other websites that are using this particular script. Web supply chain attacks are also popular because attackers don't have to affect the main website. They can go after the weakest link. Your website might be very secure, very well protected. You have a absolutely excellent security team, but you may be using a script which loads a script, from some other site that isn't as diligent as you have been. Not because they don't care, but because they simply have fewer resources dedicated to the security of that site. Unfortunately, the way that the security policy in web applications works is, in spite of you performing all of the due diligence, by virtue of loading this third-party script into your page, you are as vulnerable as the weakest link in your chain. So continuing the example that I showed in the previous slide, here on the right, I have a diagram showing the different ways in which scripts could be compromised. One approach could be to directly insert malicious code into third-party scripts, like in a live chat. Another is to go after some fourth-party script used by, a website component, like a script that is required by a video embed service, or a code dependency that is used by some analytics tool. In all of these cases, a successful attack would allow an attacker to deploy arbitrary code on all of the affected sites that transitively load it. So having arbitrary code running on your website is especially dangerous. Well, you can imagine for many reasons, but the primary thing here is that all of these scripts have the same set of privileges. Just like our first-party scripts, any of these externally sourced scripts are free to do anything from our websites. They have all got the same power. This means that attackers can use a compromised live chat widget to harvest user inputs from any form that we provide, including, let's say, login forms or payment forms. They can also add additional code to the web page, hidden, let's say, in plain sight. For example, to display a fake pop-up for phishing purposes, or to redirect the user to a different website, cause the user to download and install particular applications that have even more power. The important takeaway is that with that, one of the things that attackers regularly do is that they leak data that they collect and send it to a drop server that is under their control. Now, you can already imagine the consequences of allowing attackers easy access to credentials or PII of your users. Not only that, with strict regulations like GDPR and CCPA, this is a clear violation of users' privacy rights. When it comes to payments, for example, this directly poses a violation of regulations like PCI DSS. Not only that, it's just not doing right by your users that you desire to protect. I'm sure that when I mention supply chain attacks right now, most of you have probably thought of like the SolarWinds attack or the SolarWinds incident. So let's use the SolarWinds as an example and compare it to the web supply chain attacks. In the case of SolarWinds, it was not a web supply chain attack, but it's a similar kind of thing. We're dealing with a software supply chain attack that exploited vulnerabilities of the Orion platform. It inserted a backdoor. This essentially allowed them to deploy multiple payloads like spyware and leak confidential data on all of the affected platforms, as you can see in the diagram here. Now, of course, SolarWinds gained notoriety because it affected around 18,000 organizations, including There were federal entities. We still don't know enough about the magnitude of this attack. While SolarWinds was a fairly different kind of supply chain attack, you can easily see the similarities between that attack and web supply chain attacks. In fact, they map almost one to one. Both of these approaches stem from compromising a security weakness of a third-party vendor and then using that to deploy malicious code that makes its way down the supply chain. Once the code reaches its target, once you are able to run code on your intended client's machine, it can collect sensitive data. And then what does it do with that data? It sends it out to a command and control server and leaks it into the hands of the attackers. In both of these cases, these attacks can stay active for weeks or even months before being detected. Well, way before SolarWinds, we had already seen multiple supply chain attacks successfully breach hundreds of companies, most of which had the goal of stealing user data. I picked some news clippings here from some of the MageCart attacks, like the one on Werner Music, and other that affected, I think, 5 food ordering platforms in the US, and they leaked credit card information of 343,000 customers. I've also included some clippings here about other web supply chain attacks, like this first one where the attackers managed to backdoor the source code of the official PHP repository. So you can already imagine the extent and implications of such an attack, where we're dealing with a code dependency that is used by thousands or even millions of different websites. Finally, I've also included here CodeCov tool that is used by nearly 30,000 companies. It's a subtly different kind of attack, but again, another web supply chain attack. Attackers here leveraged a vulnerability to inject malicious code into the tool that was used by all of these different companies. And this code essentially allowed them to leak developer credentials and environment variables. So we thought. And we're now starting to hear reports that like this one here on the bottom right, where the Japanese e-commerce company discovered that it leaked thousands of customer financial records as well as a result of the CodeCov incident. Overall, what we're seeing here is a global increase in the number of leaked records year after year. And from a business perspective, leaking data is a huge problem. Like I mentioned before, a breach of compliance, like regulations like GDPR and CCPA, can result in heavy penalties. There's a $26 million fine on British Airways following the MageCart attack in 2018. Then there's also the problem of the customer backlash, rightfully so, and class action lawsuits, which leave a fairly permanent dent on the company's reputation. They can also lead to very significant legal settlements. One thing is certain, no company ever wants to be dealing with this kind of a data leak. Given a security problem of the web supply chain attacks and how they're leading to some huge data breaches, companies do need to find, like we as an industry need to find a definitive solution to this problem and ensure that customers' data, which is entrusted to us, is kept secure. But more on that. I will move things over to Pedro Fortuna. Thank you very much.
Thanks, Jasvir, for giving us such an excellent intro to this topic. So as Philip mentioned earlier, over the last 15 years, I've been focusing my research on application security. And recently, I have been observing very closely how attackers are taking advantage of the lack of client-side security to breach websites and to inject arbitrary code. Just like Jasvir mentioned, the problem of websites leaking data to the lack of web supply chain security isn't a simple one to solve, given how complex these supply chains are today. But if we're looking for a solution to this problem, it makes sense to wonder if there's a definitive cure. And yes, in theory, this problem would disappear if companies stop using third-party code altogether. However, this seems highly unlikely because right now we are seeing the exact opposite. Companies are actually relying more and more on third-party scripts, and their web supply chains are increasingly growing. Another more realistic option is for companies to find a feasible way to gain full control of their entire web supply chain in real time, including all their fourth parties. But what you have been hearing so far, you can probably tell that we are a long way from achieving these, especially because the web supply chain is very dynamic and involves hundreds of different stakeholders. So while there is not a definitive fix for this problem, companies must put in place some measures to protect their users' data. And this is why I advocate a security in-depth approach, where companies should employ several different layers of defense to defend the client side of their websites. And the good thing about the web supply chain is that, unlike what happens in other types of supply chains, the web provides us with enough building blocks to actually achieve a good level of security and mitigate most of the possible attack vectors used to leak data from websites. But before we get into those building blocks, I want to address some of the most common misconceptions about preventing client-side data leakage, which is that web application firewalls are able to prevent data leakage by blocking the connection between our website and the attacker's drop service. But while a WAF can block any unsafe connections made to our server, the backend, like SQL injection, for instance, it cannot detect anything that happens on the client side. So attacks like DOM-based XSS or web scheming typically don't make any requests at all to our server. So the WAF cannot detect it, and it cannot prevent the browser from sending this data, sensitive data, to the attacker's endpoint. I also want to address Content Security Policy, or CSP, which is a standard that is typically used by security teams to protect web pages against XSS and click jacking. In case you're not familiar with CSP, what it does is lets you define which external sources your website can connect to. You can whitelist the sources you trust, and every other connection will basically be blocked. Looking back at our diagram, CSP essentially covers the network dimension. So every allowed script will be able to load, along with any fourth-party scripts that they load themselves. CSP will then allow any type of data to be sent to these whitelisted domains. But many of these security teams that I've talked will typically understand early on that CSP is not the right answer to client-side attacks like MageGuard and data exfiltration, because there are just too many ways to bypass CSP. According to findings by Google security researchers a few years ago, around 94% of first-generation whitelist-based CSP policies are bypassable. So even if we get past that, CSP can't actually prevent data exfiltration. For instance, in the Ticketmaster example, if they had whitelisted the Inventa chatbot on their CSP, they would have ended with the web schemer anyway. And plus, the attackers can also find ways to exfiltrate data by routing it through an approved domain before sending it to the drop server. If instead we block these trusted domains, we will end up breaking things and ruining the whole application. So it's very tricky to maintain CSP. And a final showstopper for CSP is that it's not granular at all. Like I mentioned before, once we allow a certain script, it will be able to do anything it wants to. So we can prevent it from sending specific sensitive data to external domains. There's no middle ground. It's an all or nothing kind of thing. After going through all of these limitations of WAFs and CSP, it's actually a lot easier to understand the specific requirements of effectively preventing data leakage on the client side. On one hand, we need to provide visibility over what's actually happening on the client side. So we need to monitor each individual script in real time and know their specific behaviors. For instance, if a chat script suddenly starts tampering with one of our payment forms, we need to be alerted immediately about this suspicious behavior. It's also important that we know where each script originates from, so we can effectively block the attack. And in the context of preventing data leakage, an essential aspect here is being able to know if and when a certain script is sending data out, what specific types of data, and where the data is being sent out to. Without this information, we would be left clueless as to whether a certain network connection is legitimate or an attempt to leak our users' data. Visibility is only part of the solution, really. A preventive approach to data leakage requires having control of all of these different behaviors of our website scripts and being able to restrict these behaviors by default. It's crucial that we have a very granular level of control. Otherwise, we would face the same limitations that CSP has. So instead of completely allowing or disallowing a certain script from running or from connecting to an external server, we must be given a larger set of rules that we can use. For instance, we should be able to allow a chat script to run on our website, but prevent it from accessing any payment or login forms and sending any sensitive data out. So this means going beyond the network dimension and being able to define which scripts can access specific forms or call specific web APIs or have access to cookies and so on. So in a way, this is a complete shield from our client side that doesn't leave out any dimension, allowing us to control everything. Now I want to give you an overview of how we are addressing the problem of data leakage with Jscrambler web page integrity. The first step is real-time visibility. We know that any data leakage event will be associated with suspicious behaviors from one of our website scripts. By sandboxing each script, we can start observing its behavior in real time and look for these signs. For instance, we will know if a script is loading additional code, accessing specific forms, sending sensitive data out to an unknown domain. And in the case of MageCart web skimming attacks, for example, we would receive an alert that one of our scripts tried to send credit card information to a drop server. This alert would then contain the full details of the specific data that was accessed, the script behaviors that led to the attack, and the attacker's drop server. So the great thing about sandboxing is that we will be able to go beyond the network dimension and also observe if the script is mutating the DOM or attaching to DOM events. And this can be very useful to detect other relevant attacks other than data leakage. For example, preventing attacks like adware or fake pop-ups that appear on our website when one of our scripts changes the DOM. But of course, with so much data being handled at the client side, we can quickly reach thousands of detections, making it very time-consuming to go over each potential threat. This is why Jscrambler web page integrity provides aggregated views that simplify the whole process of going through data leakage detections. And these views allow us to easily filter detections by their magnitude, severity, and the affected pages. So the first image we see here is an overview of a high severity network detection that affected one IP and tried to send some data out to a suspicious domain by an XML HTTP request. The image below shows us the details of the data that would have been sent out in this request, which includes data like the user's password address, and credit card details. And we can also tell that the data was never leaked from our website because the alert says that connection was blocked. So this happened because of one of these rules that we configured to control our scripts. And this brings me to the second step, which is control. After we understand the specific threats we want to prevent and the different scripts that are running on our platform, we can define a set of rules to control their behavior. In the case of web page integrity, we provide a rule-based script fencing, which gives flexible control over these behaviors. For instance, we can whitelist a series of high-level behaviors for specific scripts. And like I mentioned before, unlike CSP, we can partially allow a script by default and block specific behaviors. The same is true for destination domains and network requests. So another example is the one we see on the left here. So in our login page, if any script has a target that equals form, it will be blocked. And this is especially useful to prevent any script from retrieving our users' credentials. So when we boil this all down, script fencing is the most effective answer to preventing data leakage on any given website. So in this slide, I tried to portray just how much control we get from script fencing. So by sandboxing our live chat scripts, we can set a rule that only allows it to run on the user page and prevents it from adding fourth-party code. So then we can go one by one in each client-side dimension. So first we can prevent this script from tampering with other JavaScript code on our website as a general rule. When it comes to forms, we can allow it to only access a specific form and only the username and email fields. We can also prevent it from accessing any cookies on the user's locals and the user's local storage. So then we can also define which event handlers this script is allowed to set. So which in this case, it can only set event handlers on the user's form and only on the onSubmit events. So I decided to be more permissive in terms of how this script can mutate the DOM. And so I've placed no restrictions there. And I'm also allowing the script to call any web API. And finally, on the network dimension, I'm being very careful and only allowing the script to contact a specific endpoint. And even then, the JSON object can only contain two fields, which are the username and password. So this really shows the granularity that we're aiming for with web page integrity, which addresses the limitations of other approaches that are based on CSP, for instance. It's just like I mentioned earlier, solving the problem of web supply chain attacks requires companies to have full control over their web supply chain. And the flexibility of web page integrity goes a long way into providing that much needed level of control because it allows creating high-level rules that will apply to any script, whether it's a third party or a fourth party, and even if its behavior is constantly changing over time. Well, I think now it's the perfect time to move things over to Don, who will talk us through a demo of web page integrity in action. So Don, feel free to take it from here.
Thanks, Pedro. Really glad to be joining you and Jscrambler today on this webinar to discuss what I believe is one of the biggest business problems of this decade. My job for today is to demonstrate Jscrambler web page integrity in action. And what better way to do that than simulating a data leakage attack on a banking platform? As you can see, here we have your run-of-the-mill web banking application, and right now I will be navigating it just like any end user. Let's just say I want to log in and check my account balance. I will do this using the login form here. And this leads me straight into my account page where I have all my details, including my balance and my credit cards. That's it. A straightforward session that took me less than a minute. Everything seems fine, so I just go ahead with my day. Little did I know that all my data was just leaked into the hands of attackers simply because I was at the wrong place at the wrong time. What happened is that an attacker somehow managed to leak my data through the bank's website. And sure enough, if we go peek into the attacker's drop server, we can clearly see all my data. Everything from my email and password to other sensitive information like my address, phone number, and credit card details. Now, of course, as an end user, I would have no idea that my data was leaked. But the problem is that the bank will probably also be left in the dark because this attack didn't involve any type of breach to the bank's systems or its servers. What happened here was a typical web supply chain attack that took place entirely at the client side when I navigated the bank's website using my browser. To make it easier for us to see what happened behind the scenes, I was actually running Jscrambler's web page integrity on the session I just showed you, but I disabled all the blocking rules so that the attack could still happen. Let me jump right into the Jscrambler dashboard to see what types of malicious behavior were detected. All right. In this first screen, I can see some real-time alerts that were classified as being high severity. When it comes to data leakage, we're especially concerned with networking decisions or detections, especially those that are made unknown or suspicious external domains. In this case, I can clearly see that there was a networking request to maliciousAPI.jscrambler.com. Let me check for more details about this request. I can see that a request happened on the accounts page, and if I move over to the details tab, here's where I find the drop server that received the data of this network connection, along with the data that was specifically sent out to the external domain. And I would immediately tell that this doesn't look good because the data contains things like user's email, password, address, and credit card information. There's no question to me that I'm dealing with a data leak. The question remains, however, is how is this data leaked? And to answer that, I just need to go to the sources tab here, and there you go. This is third-party justchat.js script that I'm running on my website as a live chat plugin. And on my right column, I can see the different functions that were used by the script to leak the user's data. Let me just check the other security alert. This one is fairly different. First, because it's classified as a tampering event, more specifically, a code poisoning event that happened on the onSubmit event handler of one of my website forms. Let's open this up to check the details. I see this happened on the login page, and moving over to the details tab, I get some additional information. Since this is a tampering alert, there are some details about the code that were changed on the website. And I see that something changed the onSubmit event listener on the login form so that now it stores the username and password on the user's local storage. This tactic is commonly used by attackers to save data before leaking it through XHR. Finally, on the Sources tab, I see that again, this malicious behavior came from the Just Chat script. All right, it seems like the data leakage mystery is solved, and everything we just saw just comes to show the level of visibility that Jscrambler provides. We get real-time alerts of any suspicious behavior along with the script that is behind it. And in the case of data leaks, it clearly shows what type of data is leaked and where the data was sent to. But like Pedro mentioned, visibility is just half of what we need to tackle the problem. So now let's look at the other key dimension, which is control. I need to go to the rules page. And so here are the rules I mentioned, which again are all disabled. Let me go through each rule to explain some different preventive approaches we use to prevent this type of data leak. My first rule here, which I aptly named profile protection, is a high-level rule and it's very straightforward, as we will see. If I scroll to this middle section here, I see that the different combinations of conditions I can use to control the behavior of one or more of my website scripts. In the case of this rule, I am applying it only to the account page. And I left the resources section blank on purpose so that the rules apply to every single script running on the account page. Finally, I can specify the pattern of behaviors that I want to control. In this case, what I'm saying is that I want to control every network request whose payload contains any of these parameters: a username, password, email, address, or credit card. There are a lot of other events I can set here to specify different types of behavior, but in this case, I want a simple rule that's specifically aimed at preventing leakage of sensitive data. The only thing left to do is to choose an action to trigger whenever those conditions are met. Since I want to use a preventative approach, I've set it as block. Reading my rule again, it simply says, if any script tries to do a network request containing these types of sensitive data on the profile page, block the network connection. It's a high-level rule that will give me some peace of mind and allow me to protect the data that is present on the user's profile page. Now let me go back to the rules screen to go over the second rule I've created. This one I have named form protection, and it's pretty self-explanatory. So again, as a preventative measure, I want to make sure that no script can tamper with any of my forms. So in the events, I am using two conditions, which is whenever the target equals forms and when the target events are on submit, on click, or click. And again, I'm using block as the action to be triggered whenever those conditions are met. In a nutshell, this works like a form jacking protection, which is very handy to prevent attacks like MageCart web skimmers, which target payment forms, or any attack that targets a login form, for instance. Now, I've covered two of my high-level rules. Let's look at a more specific one. Going back to where I have another rule called just chat restrictions, looking at my rules conditions, it's clear that the rule is aimed at a specific resource, which is a third-party live chat service that I'm using on my banking website. Here I'm just specifying the URL of the script itself, and then instead of just completely whitelisting or blacklisting the script, I can specify what specific behaviors I want to allow or disallow. What I have here is simply that whenever the script attempts to perform a network request whose payload contains username, password, email, address, or credit card, I want to block that connection. This also makes sense from a preventive approach because I know that the live script doesn't need to send any of these types of data out in order to work properly. In a way, this helps me ensure that by using this third-party script, I'm not jeopardizing my compliance with data protection regulations because the data will never be sent out. Great. Now I just need to go back and enable each of these rules and protect the Jscrambler agent. And that's pretty much it in terms of configuring Jscrambler. Now all that's left for me to do is replicate the user's session and see what happens. I'll refresh the page before starting, and now I'll go ahead and do the same steps. Let me go ahead and log in. And now I get my account balance, and that's it. Let's take another look at the attacker's Dropbox or drop server and refresh the page. I can see the data that was sent on my previous session some minutes ago, but that's it. No new data has been received since. All that's left to do is to see the alerts on Jscrambler's side. And now going back to the feed, I see similar alerts, but they are clearly marked as blocked. Both the data leakage on the profile page and the tampering of the login form were successfully mitigated by Jscrambler, and the user's data was kept secure. This pretty much sums up how much Jscrambler web page integrity addresses both the visibility and control dimensions that are needed to mitigate data leaks. So I think that's a good place to stop this demo and move things over to Pedro again. Thank you.
Thanks, Don. So I just want to wrap things up with some final thoughts. As we have seen, the average website today is a mashup of client-side code, which creates a huge security blind spot. The problem here is that attackers are taking advantage of that blind spot to leak data from websites. Web supply chain attacks like MageCart, for instance, can go undetected for weeks or even months. Because these data leaks means a breach of compliance with regulations like GDPR, these attacks may result in heavy fines for companies and frequently lead to a decline in the customer's trust. So the solution to these attacks is definitely not using a WAF, because WAFs don't deal with client-side attacks. And as we saw, CSP-based approaches are also not the answer, because they don't provide the needed granularity and flexibility it takes to mitigate attacks, and they can be most of the time easily bypassable. So the two key ingredients here are visibility and control of client-side scripts. And this is precisely what our web page integrity solution provides. On one hand, real-time visibility of data leaks by sandboxing each script. On the other hand, rule-based script fencing, which can prevent any script from leaking data. When combined, these approaches put the control of the web supply chain in the hands of the companies, allowing them to effectively prevent client-side data leaks. Well, that is all from my side. Thank you.
Thank you, Pedro. Well, we're wrapping things up, but before we finish, I want to remind everyone that you'll receive an email with our datasheet on web supply chain attacks, which provides an overview of the topic that we've discussed today. As I mentioned earlier, if you have any specific questions, feel free to reach out to us using the email you see here. We will also include details on how you can get started with a free web application inventory, so keep an eye out for your inbox. And that's it from me. Thanks everyone out there for joining us today, and see you next time.